Welcome back to the deep dive. Today we're getting into what feels like the ultimate engineering illusion, the simple machine.
Right.
Specifically, we're looking at a pulley system. You see this huge block and tackle setup, and suddenly you can lift something that seems impossibly heavy with, surprisingly little effort.
It really does feel like you've found a secret cheat code for
It
physics.
does. So the question is, are you actually cheating?
Well, that's the core paradox, isn't it? When you just look at the raw mechanics, the machine lets you apply way less force than the actual weight of the load.
Okay.
So if I'm lifting a 200 Newton object, but I only have to pull with, say, 40 Newtons, my gut just tells me I've saved energy somehow.
Of course.
So our mission for this deep dive is to get into the data from an ideal pulley system lab simulation and prove pretty definitively that physics doesn't really allow for shortcuts. You're simply trading one thing for another.
A trade-off. Okay, so let's establish the fixed constants we're working with, because every single trial in this data set is designed to do the exact same job. This is our baseline.
Precisely. This is the non-negotiable part of the task. We are lifting a constant load mass of 20 kilograms.
Okay, 20 kilos.
And in the world of physics, that translates to a resistance force, we'll call it the NRUR rule, of $200 newtons, and the target lift height, the resistance distance, or a baller, is fixed at 5 meters.
Which means the total work we have to do, the work output, or Tau, is always the same. It's immutable. Work is just force times distance.
Exactly. 200 newtons multiplied by 5 meters gives us 1,000 joules.
1,000 joules.
And that 1,000 joules is the immutable core of the task. That's the energy cost. That's what you have to pay every single time to raise that 20-kilogram load 5 meters into the air.
Doesn't matter if you use your bare hands or some super complex machine.
It does not matter. The universe demands 1,000 joules.
So that's set in stone. The variable we're actually playing with, the lever we're pulling here, is the pulley system itself. And we measure that using the ideal mechanical advantage, or IMA.
IMA is our main variable. And in a perfect, a completely frictionless pulley system, the IMA is beautifully simple. It's just the number of ropes that are actually supporting the weight.
So if I see a piano dangling from 5 ropes that are all pulling up on it?
Your IMA is 5. You have 5 times the advantage. Simple as that.
Okay. And our simulation data, it covers a whole range.
Yeah, it covers the whole spectrum. It starts at an IMA of 1, which is basically just a single fixed pulley. You're just lifting it directly, all the way up to an IMA of 5.
So IMA 1 is like doing it the hard way.
And IMA 5 is using a sophisticated block and tackle system that makes the whole thing feel easy.
Right. So the big question for you listening is simple. We know the machine reduces the effort, but by how much, and what exactly is the price physics demands in return?
Let's start with the good part. The immediate benefit, the reason anyone even uses a pulley, the force reduction. We're tracking the required effort force, the fourth NO, which is just what you have to pull on the rope.
And when we started IMA 1, the baseline, it's brutal.
Yeah.
You need 200 newtons of effort force. You're fighting the load 1-to-1.
There is no advantage. But the second we add just one more supporting rope moving to IMA 2, the effort force drops dramatically.
How much?
Right down to 100 newtons. The force required is instantly cut in half.
Wow. Okay, so that's why sailors and construction workers love these things. An impossible job becomes just a difficult one.
Exactly. And the data shows this isn't random. It's perfectly tied to the IMA. If you jump to an IMA of 4, the effort force required is 50 newtons. You've cut the force you need by 3/4.
And what about the extreme end, the really complex system?
When we hit IMA 5, that 200 Newton load is now spread across 5 ropes. So the required effort force, the phi revoltar, it just plummets all the way down to a mere 40 newtons.
40 newtons, that is, what, an 80% reduction in the muscle you need?
It is.
So that immediate benefit, going from a 200 Newton strain down to a 40 Newton pull, that's the payoff for using a more complex machine. It makes the job feel completely different.
It absolutely makes the job feel different, but that's the illusion. The physics accountant is knocking on the door now.
Here's the catch.
Here's the catch. You didn't just save 160 newtons of force, you just shifted that requirement somewhere else. If the force has been reduced by a factor of 5, there has to be a cost factor of 5 hiding somewhere else in the equation.
And that, of course, brings us to the cost, the other side of the trade-off. We need to look at the effort distance. How far do we actually have to pull that rope?
Let's track it. So remember, the goal, the dollars, is always to lift the load 5 meters. At IMA 1, you pull 5 meters of rope, the load goes up 5 meters. Simple. High force, short distance.
Okay, now let's jump to IMA 2, where we cut the force in half down to 100 newtons. What does the data show for the distance?
The effort distance instantly doubles to 10 meters.
You pull twice as far.
We have to pull twice as far to get the same 5-meter lift. This is where the trade-off becomes really tangible. You're trading sheer power for endurance.
And the more ropes you add.
The more rope you have to pay out. At an IMA of 4, you're pulling 20 meters of rope to raise that load just 5 meters.
And at the top of our test, IMA 5,
Yeah.
where we only needed that easy 40 newtons of force, the distance must be huge.
It explodes. You have to pull the rope for 25 meters.
25 meters to lift something 5 meters.
Yep. So the key takeaway here is the perfect counterpoint to the force. As IMA increases, the effort distance you have to pull increases proportionally. We went from pulling 5 meters to pulling 25 meters.
This is where it stops being just interesting and becomes, well, almost elegant. The ratio between the distance we pull and the distance the load moves isn't some coincidence.
No, it's the defining mechanism. It is the mathematical proof of the trade-off.
So let's look at the numbers.
Okay, take the data for IMA 5. The effort distance was 25 meters. The resistance distance, the lift, was 5 meters. What's 25 divided by 5?
It's 5.
It's exactly 5. The ratio of the distances is the IMA value.
So the ideal mechanical advantage, the number of ropes, is precisely equal to the ratio of how far you pull versus how high it goes.
Yes. The IMA doesn't just reduce the force, it dictates the exact required distance you have to travel to keep everything in balance, to maintain the conservation of energy.
Which perfectly sets us up for the big aha moment.
The ultimate realization. Conservation of work. If we multiply our tiny force by our huge distance, what do we get?
This is where that illusion of cheating physics just completely collapses. We have to compare the work input, what we put into the machine, with the work output that required 1,000 joules.
Let's look at the extremes again. At IMA 1, the work was easy. 200 newtons times 5 meters.
1,000 joules of input. It matches.
It matches. Now, jump to that high advantage IMA 5 system. We only used a comfortable 40 newtons of force, but we had to pull for 25 meters.
40 newtons. Multiply by 25 meters.
Okay.
It's 1,000. It's exactly 1,000 joules.
It's exactly 1,000 joules. Every single trial in this simulation, from IMA 1 all the way to IMA 5, resulted in a work input that was perfectly equal to the work output.
Always 1,000 joules.
Always.
Yes, that is powerful. This data just explicitly confirms that unbreakable principle that work is conserved in an ideal machine. The machine does not save you energy.
It can't. It only changes the form in which you apply it. It's like an energy translator.
It translates a need for a big, short burst of force into a long, slow, low-force effort.
Exactly.
Okay, but hold on a second. If I'm pulling rope for 5 times longer at IMA 5, I am personally spending more metabolic energy over that longer time.
Right.
Isn't that a form of energy loss for my body?
That is a fantastic point, and it's a critical distinction between textbook physics and physiological reality. From a strict physics perspective, the work input, the force times the distance, is the same. But the chemical energy your body burns, your metabolism, is definitely higher over that longer period. But the machine's required work input, the mechanical energy that actually moves the load, that stays at 1,000 joules. The machine only cares about the mechanical work, not your heart rate.
So the physics equation is balanced, even if the person pulling the rope feels more tired from the duration. The mechanical work required is constant.
Exactly. And that brings us to the synthesis, right? How do we sum up this core force-distance trade-off for everyone listening?
I think it's simply that inverse relationship. You have to maintain that constant product of 1,000 joules. A simple machine just lets you choose between two options: a huge force over a tiny distance or a tiny force over a huge distance.
You can't have both. The product is constant, but you get to pick your path. And with a pulley, increasing the IMA is you explicitly choosing that small force, large distance path. You're trading muscle strength for time and endurance.
Which brings us to the practical application. Why would I ever choose to pull 25 meters of rope instead of just 5 if I still have to do 1,000 joules of work? When is that cost worth it?
You choose the high IMA, the low force path, when it's the only path that makes the job physically possible for you.
Meaning, if I can't lift it directly.
Right. If you cannot personally exert 200 newtons of force, maybe your maximum is only 150 newtons, then with an IMA of 1, that load simply doesn't move. The job is impossible.
So the goal isn't saving energy, it's just enabling the task.
Yeah.
I might be able to strain and pull 200 newtons for a second, but I can easily hold 40 newtons for a long time, long enough to pull all 25 meters of that rope.
That's it. The high IMA reduces the required effort to a manageable, sustainable human scale.
Think about construction rigging.
A perfect example. Lifting a steel beam up 10 stories, you don't care if it takes 15 minutes of hauling or that you pull hundreds of feet of rope, as long as the force needed is low enough for a couple people to do it without a crane. The trade-off is absolutely worth it.
Or sailing. Those block and tackle systems are everywhere. Hoisting a huge mainsail against the wind takes immense force.
You could try to just yank it up, but you'd fail or injure yourself. So you run the rope through a bunch of pulleys, you accept the distance penalty, you pull and pull and pull in exchange for a massive reduction in the tension on the rope. It makes the impossible possible.
It's the ultimate engineering concession to human limits.
That's a great way to put it. The machine doesn't change the laws of physics, but it manages the input variables to fit inside the constraints of the person operating it. That's its whole purpose.
And the data just brings it all home. Whether we yank that load straight up 5 meters or painstakingly pulled 25 meters of rope with that IMA-5 system, that 20-kilogram mass required exactly 1,000 joules of mechanical energy.
The pulley just served as the translator. It made the application of that 1,000 joules manageable.
So this leads us to one final provocative thought for you to take with you.
Right. Our whole analysis, all of this perfect math, was based on an ideal machine.
A frictionless world.
A frictionless world where the work you put in exactly equals the work you get out. 1,000 in, 1,000 out. Perfect 100% efficiency.
Which, as we all know, does not exist outside of a textbook or a computer simulation.
Exactly. So what hidden energy cost, a cost that we didn't account for here, must exist in every single real-world pulley system. If you did this experiment with actual ropes and metal wheels, you'd find that to get 1,000 joules of output, you'd have to put in, say, 10, 50, or 1,100 joules of input.
So where does that extra energy go?
Where does that difference vanish? What does that missing, non-useful energy represent in the real world? Think about the sound of a rope groaning over a pulley, or the heat you might feel in the axle after a long hoist. That's the messy, unavoidable price of reality.